Hello, everyone. We are going to start our conversation today on chemical hazards by focusing in on chemical toxicity. And to help begin this conversation, we're going to start by talking about one of the more famous cases of a chemist being killed due to chemical toxicity. And that's the case of Karen Wetterhahn. So she was a professor at Dartmouth College and was considered one of the foremost experts in metal toxicity. And as part of her research, she was preparing an NMR sample of dimethylmercury. Well, it turns out that when working with this, she managed to spill a single drop on her glove. And she was indeed wearing gloves, but only a single layer of latex gloves, which it turns out the dimethylmercury can permeate straight through. And so it permeated through her glove, through her skin, and ended up spending the next 10 months doing neurological damage. Eventually, after 10 months, she ended up passing away. And again, she was doing everything as she should have, wearing gloves, being precautious, but not being aware of the exact nature of the route of entry of a chemical can often be quite catastrophic. Now, most chemicals are not as dangerous as dimethylmercury. It's really one of the poster children for toxic chemicals. But it illustrates an important point that you need to make sure that your precautions match the exact description and problems of the chemical you're working with. So today, while we're talking about, we're going to start by talking about chemical hazards, which we're going to end up splitting up into four major categories. The first is toxicity. So these are often marked with the globally harmonized classification system, which we're going to talk about later, and can be thought of as acute or fatal toxicity, carcinogens or general health hazards, irritants, and more environmental or aquatic toxins. So we have also flammability. So go figure, certain things can catch on flame, which can be sometimes related to reactivity, which is often marked by the signs of oxidizers. So these are ones that can catch fire when combined with reductants, and explosive compounds. So these are ones that can usually react with themselves quite vigorously to produce excess pressures and thus explosions. And corrosivity. So this has specific dangers such as skin corrosion and eye damage, but also goes into surface corrosion. So we're going to be talking about these three later. Today, let's go ahead and focus in on this toxicity issue. Now, one of the important things to be aware of when we're talking about the toxicity of compounds is it turns out that there are a lot of chemical compounds out there. In fact, there's over 120 million registered compounds with the ACS. And it turns out that most of these are going to only have rudimentary information about their safety. Now, 80,000 of these are registered for use and production in the US, and these ones we're going to know a lot more about their toxicity, but still may not all be well studied for potential dangers. And it turns out that the EPA has only evaluated a small subset of these chemicals for potential use in industry and environmental and health damage. So again, we may not have as much information as we'd like about all of the chemicals you may be working with. But even with the greater 120 million, hopefully you're going to be able to collect some information so you can at least get an idea of what type of health hazards a chemical will pose. And if you don't know, always try and play it safe. So one of the first things I want to talk about with toxicity is a very important idea. It turns out that all things are toxic in sufficient quantity. This includes things such as water or salt. If you ingest too much water, it turns out that it can actually kill you. So, for example, it turns out it would take about 5 pounds of sugar to constitute a lethal dose. In contrast, 2 pounds of salt, 6 liters of water, 14 grams of aspirin, or about one castor bean. So the real question in toxicity is going to be ending up lying in the details, and these can actually be really important. So one of the first important things that a lot of people forget is route of entry. So there's going to be four major routes of entry for toxin. Inhalation, so breathing it in. Ingestion, so consuming it orally. Absorption, typically through the skin. Or injection, so injecting straight into your bloodstream. And it's worth noting that the route of entry makes a huge difference. A great example is, let's say I've got, say, 20 milliliters of water. It's completely safe if I drink it. I can go ahead and bathe in 5 gallons of it with no issue. But if I try and inhale, say, 20 milliliters, I'm going to have a bit of a problem because I'll be choking. And injecting it into my bloodstream is right on out, because that's going to play merry havoc with my with the salinity of my blood. So again, just because something is safe for absorption or ingestion doesn't mean that it's safe for inhalation or injection. So this is something you should always try and keep in mind. Similarly, the dose is also a major problem. So and this is the one that people tend to focus in much more on, in that the amount of a toxin is really is one of the major controllers of what makes it toxic. Now, it is worth noting that most metrics are going to be based either on the mass of the person. So if you are a lighter person, they assume a lighter dose of a same toxin will be dangerous. But it can often be based on environmental concentration, say as concentration of the toxin in the air. And we're also going to find great differences depending on the duration of exposure. Some toxins are only dangerous under acute circumstances, so under high short-term doses. And there's some toxins which are much more dangerous on a chronic basis, such as things like metallic mercury, which would take a large dose to be acutely dangerous, but low doses over long periods of time can pose quite major issues. And then the final thing that's important to keep in mind is going to be the nature of the toxin. So how is it going to affect your body? What organ system is it going to do damage to? And this can be especially important if you have somebody with, say, diabetes who already has a compromised liver or kidneys. So again, some people will be much more vulnerable to certain different types of toxin, simply based on what organ system it affects. And this will also end up being related to, say, route of entry. So when we're talking about hazardous compounds, the classic way that people evaluate toxicity is just by looking at acute toxicity. So this is just going to be looking at short-term dosages. And they do this via what's called the LD50, or the lethal dose 50%. And it's a measure of how much of a substance is required to kill 50% of the population it's exposed to. And this is typically based on a rat or mouse model, where they evaluate the amount of toxin that it takes to kill a rat on a milligram of toxin per kilogram of rat. And this tends to scale fairly well to humans, but it does run into some issues of rats are going to be less responsive to certain types of toxins, and more responsive to others. So we typically split our hazardous materials into three major categories. So first of all, we have very toxic. So these are compounds with an LD50 of less than 25 milligrams per kilogram. Then we have, this includes things like botulinum toxin, which is quite toxic at 1 milligram, and our good old friend cyanide, which the movies love, which is toxic about 10 milligrams. We also have just generally toxic and harmful compounds, which you can be exposed to, but make sure that you don't get too high of a dosage. And this includes things like nicotine and caffeine. And though I know you're probably getting through this semester based on caffeine, watch out. Too much caffeine in too high of an acute dose can cause heart attacks. But we also have materials that we might not think of being quite so harmful, but in high enough dosages can actually be fairly dangerous. So this is things like aspirin and argon. So let's go ahead and try and compare these LD50s to maybe some common compounds. So if I go ahead and say scale up an LD50 for me, who weighs about 160 pounds, what would it take to end up killing me? So I could be, I'd reach the LD50 with about 5 pounds of sugar, as sugar has an LD50 of about 30,000, so fairly safe. We also have about 2 pounds of salt with an LD50 of about 12,000, again, still fairly safe. Now, I could also be poisoned by drinking 6 liters of water straight, as that would more or less ruin the balance of salt in my blood and cause me to entertainingly dehydrate all my cells to overinflate because the osmotic balance would be out. And this would be, again, 6 liters of water with an LD50 of 90 milliliters per kilogram. And again, one of those things to watch out. The units will occasionally change. And aspirin, with its LD50 of about 200, it takes about 14 grams of aspirin to kill an average human adult. Whereas once we get to ricin, which is found in some plants, it has an LD50 of 20 milligrams, so under the very toxic level, and 1.4 grams of ricin would typically kill an average adult, 3.6 grams of nicotine, or one of the chemical neuroagents I studied during my graduate work, VX nerve agent, which has an LD50 of 0.04 milligrams per kilogram, meaning that to kill an average human, you need about 2.77 milligrams. So pretty much just the drop. So again, all of this is fairly useful if I'm just looking at acute toxicity. So these are the limits of how much exposure I should never even try and approach. If I want to, we don't ever want to get with even shouting distance of an LD50. However, most of the time what I have to worry about much more is chronic toxicity. So not acute exposure or one-time exposure, but if I have to go into work every day, what sort of chemical levels might actually start posing a problem? So it turns out that a good source for a lot of these numbers comes from OSHA, which pretty much sets all work safety standards. And so it sets a series of legal safe limits for chemical exposure on the basis of 40 hours a week exposure, 50 weeks a year. And these are typically reported as permissible exposure limits and often acronymed as PELs. And the idea is that most of your chronic exposure is going to come through airborne exposure. So it lists most of these as airborne concentrations, which should be theoretically tested by any business which may be potentially exceeding these. And you can find a full list of PELs from the OSHA website here, and I have a link to it also on the Blackboard page. However, it does take a while for OSHA to keep up to date with the latest research of what typical toxic levels are. So if you want a more up-to-date version of the PELs, they're often provided by the American Conference of Governmental Industrial Hygienists, ACGIH, and they typically will report these values on their own websites, but they are also available for many compounds on the OSHA website, and they're reported as threshold limit values. And so for most operational guidelines, these are typically the levels that everyone's trying to avoid exceeding. And again, all exposure should try to be held below the threshold limit values. So if you want a good metric of what you should try to be avoiding, I encourage you to look up the TLVs for whatever chemical compounds you think you might be exposed to. And again, I tend to find that these chronic levels are much more useful measures of acute toxicity. While I definitely don't want to exceed my LD50, the TLVs are much more useful. However, it turns out that I might want to have a acute toxicity measure that isn't just going to say this is the level at which you die, but this is the level at which, even on a short-term basis, you're going to just have problems. And these are often provided as either the short-term exposure limits or ceiling limits. These terms are often used interchangeably. And again, these are provided on the OSHA website. And these are essentially good guidelines for the maximum safe concentration. Though again, like the PELs, the values can be a little bit out of date. So let's go ahead and take a look at some representative chemical compounds and look at their PELs, their TLVs, and their ceiling limits. So we may have something like acetic acid. So this is our good old friend, vinegar. And it turns out that if you get too high of a concentration of acetic acid in the atmosphere, it can start doing some long-term damage. And so this is a case where we find the PELs from OSHA and the TLVs from industry in fairly good agreement. And not too surprisingly, the ceiling limit's only a little bit higher. So you can exceed the 10 ppm, but not by much on a short-term basis. However, I tend to find ammonia and carbon monoxide are also a very good demonstration of how these three values differ. So we find that both ammonia and carbon monoxide have PEL values of 50 ppm, but increased modern research tries to put these values at about half that amount, essentially saying that these numbers are kind of out of date and still unsafe. And you can specifically see this with the case of ammonia, where the ceiling limit is lower than the PEL. So while you can exceed 25, it's really not by much. Whereas you got a little bit more wiggle room on carbon monoxide, but please try and don't risk it with carbon monoxide. It's just kind of dangerous. And again, we see similar trends with phosphine, which is a quite dangerous gas present in the synthesis of a lot of pesticides. And also we occasionally will find values not present in PEL or in ppms, but instead in terms of mass per volume. This is often the case for heavier compounds, which tend to behave as particulates. So the specific case I'm looking at is Trinitrotoluene, which you may know a little bit more as TNT. And again, we tend to find, again, PEL values are a little out of date, and modern industry sets safe values much lower. So again, one of the things I want you to note about some of these values is, again, PELs are very useful, but again, TLVs probably are a much better representation of safety, as demonstrated by how many times the PEL actually exceeds the short-term exposure limit or the ceiling limit. And again, we may also find that based on chronic exposure, there may be some things that were a little bit unexpected. For example, ammonia and carbon monoxide are considered about as toxic. And we also have things like acetic acid turns out to be more toxic, at least on a chronic level, than, say, carbon monoxide. But again, it is worth noting that do not play around with any of these chemicals. And one of the reasons why carbon monoxide is so dangerous is, unlike acetic acid and ammonia, it doesn't have a liquid form. So again, these can be some useful metrics to make use of in the future. And if you end up working with another set of compounds, I highly encourage you to look up, especially the TLVs and ceiling limits on OSHA or through another industrial website. So again, one of the other things that's very useful is to measure exactly how these compounds can interact with their body. So this can be a combination of route of entry and considering what organ system the toxin is going to attack. So I'm going to break these up into a series of example categories. So the first of which is allergens, which essentially just trigger an immune response. And this can be a lot more person specific. But some common examples that you may end up encountering in a typical lab include things like a latex allergy, at which point be very aware of what gloves you're working with. Aspirin, which can be a little bit problematic if you're working with powdered drugs in a biolaboratory, but also things such as nickel. And I myself am allergic to corn, which will keep me away from a lot of biolabs. And it's not uncommon for people when they're entering research to actually have to switch labs that they're working in because they're exposed to some sort of unknown allergen. So if you notice redness of skin, irritation of lungs, or general not feeling well when entering a new lab, it might not be in your head. Be aware that there may be some sort of allergen exposure that you weren't expecting. We also have asphyxiants. So these essentially are anything that stops air uptake. And they can essentially work by three major approaches. First, they can displace O2 on a cellular level. So they'll actually, say, block uptake of O2, say, on your heme groups in your blood. And so great examples of this include, say, carbon monoxide, which displaces O2. They can also essentially block enzymatic functions that process how oxygen ends up being used inside your body, and this can include things like hydrogen sulfide. But it can also just simply displace O2 in the atmosphere. So a great example of this is N2. And one of the things you should watch out with asphyxiants is you won't necessarily notice that you're being asphyxiated by essentially the classic pain of suffocation. Because it's worth noting that how your body registers suffocation is not by a lack of O2, it's by an excess buildup of CO2. So if you can still exhale fine, but you can't process blood or process O2 either on a cellular, enzymatic, or just by breathing it in, you won't notice anything. So this is one of the reasons why I have indeed had carbon monoxide poisoning, and you don't notice anything until your muscle groups give out. And one of the most famous examples is a NASA clean room where a group of 6 scientists were working in a clean room that had O2 and N2 pumped into the room, and then CO2 scrubbed out. Well, it turns out that the O2 line failed, but the N2 line worked just fine. And the scientists promptly all fell down and fell asleep and promptly passed away simply because there wasn't any O2. Well, there was still plenty of O2, and it was doing a great job of displacing any oxygen from the atmosphere. So again, one of the things you should watch out for asphyxiants. We also have diuretics. So this is going to be anything that can increase urine production, which essentially tends to work by draining all of the salts out of your body. So this can include anything as benign as caffeine, which tends to be the reason why if you have a lot of caffeinated drinks, you feel the need to urinate all the time. Make sure that despite the fact you're drinking caffeine doesn't mean you shouldn't be drinking other things to replace those salts. But it also tends to be very common among a lot of plants, such as digitalis, also known as foxglove, where you essentially tend to poop yourself to death. So, bad way to go. And again, watch out, this is common in a lot of biological compounds. We also have heavy metals. No, this is not Metallica. These essentially often work by displacing their lighter analogs. For example, you may have something like arsenic, which can replace nitrogen or phosphorus in your biological systems, and lead, which can replace can often replace many carbon-based compounds. And we've already talked about the problems with radium displacing calcium in the bones. So one of the biggest reasons you have to worry about heavy metals is less due to their acute toxicity and more due to their chronic toxicity, as they tend to be very good at building up in the body until they reach deadly levels. And again, certain types of heavy metals, due to their surprisingly nonpolar nature, depending on what compounds they may be present in, do have the ability to absorb through skin, such as alkyl mercury species. Then we have lacrimators, which is kind of a fun word, but is another way of saying things that produce are tear-producing agents. So these are ones that are going to irritate your eyes and make you cry. And so this can include things such as onions and their sulfonyl propane. And you might not think of these being tremendously dangerous until you think about what danger you could get into a lab if your eyes are blocked up by tears, as well as this tear production can end up acting as a entry mechanism for certain other compounds. So while lacrimators may be one of the less dangerous of our toxic compounds, they're still nothing to be sneezed at. Well, they might make you sneeze. Then we have organic solvents. So this can have a great deal of various approaches. One of the things to note is due to their nonpolarity, it's common for some organic solvents to be able to permeate skin, and many of them actually can be quite volatile, so can get into the air, where they tend to do a lot of lung damage. One of the causes for a lot of the organ damage from organic solvents is their tendency to dry out a lot of tissues, which is the major way they can do a lot of lung damage, as they dry out your lungs, causing cellular damage. But they're also very good at blocking up kidneys and other toxin-clearing organs such as the liver. And it turns out that they can also do a fair number of other damage if they're able to block specific enzymatic functions, such as the ability of VX to interfere with your body's ability to relax muscles. So you essentially die in muscle paralysis. And that brings us to the last group of neuro inhibitors. So these can be anything from specific organic compounds to heavy metals, which essentially just block neurological function. And again, one of the big things you have to watch out for is going to be things like synergistic effects. So it turns out that when you combine several different toxins, you may get unexpected results. So a good example is that it turns out if you have, say, a chlorinated solvent, so a nice chlorinated organic solvent, and you end up drinking alcohol afterwards, that chlorinated solvent actually becomes more toxic as it essentially increases bioavailability and it's easier for the chlorinated solvent to interact with targeted systems. In comparison, it turns out that some of these toxins can actually be antagonistic. So a way to think about that is that they may end up canceling each other out, or one toxic effect may block another. A great example is that if you have certain types of toxins, you actually might want a lacrimator to cause tear production to flush out any toxins in your eyes. Another famous example is that it turns out if you have methanol poisoning, sometimes doctors will essentially get the patients drunk as the alcohol can displace the methanol and dilute the methanol in your system. So you're still going to get yourself good and poisoned, but you might not die. So that brings us to our end of our discussion on toxicity. Next time, we're going to be talking about flammability, because who doesn't like some fire? Until then, take care.